locating on the region R such that the x coordinates is between 0 and A, and the y coordinates is in between 0 and B. Okay, in the x y plane. When at rest, okay, at time t. And the displacement in x, y, t will be governed by a two-dimensional wave equation on R on the rectangle alright, so U is equal to C square U plus the point xy is in R and the C square is the ratio between the tension of the membrane and the mass density, and we assume that the membrane has homogeneous mass density. Okay, and with a boundary condition on the boundary of the rectangle. Okay, so this is 12.9.1. That's x, y, t equal to 0 for all x, y in the boundary of R, and for all t equal to 0. Okay, so so this boundary condition, which indicates that the membrane is fastened along the boundary of the rectangular membrane. And we also have two initial conditions. Okay. One is that the initial displacement at the time of 0 x equal to f of xy which is the initial displacement, and the partial derivative of u with respect to term u sub t is equal to g of xy at time equal to 0. Okay, so which is the initial velocity. Okay, so we have one boundary conditions. So alright, so we will solve the two-dimensional wave equation by two successive separating variables. Okay, so first of all, so we let u of x y t equal to f of x y and g of t. So we separate the spatial variable and the time variable, right? And substitute into to the two-dimensional wave equation to obtain f of g dot dot. So that makes the second derivative of g with respect to t equal to c square and f sub xx. So this is the second order partial derivative of f with respect to x, times g plus f of y times g. Okay. Okay, and so if we divide c square times f times g on both sides, we have g dot dot c square of g equal to f and fxx plus fyy and equal to k. Okay, where k is a constant. Okay, so this is the the first separating variables. Alright, and so that's, we obtain one ODE G dot dot minus K C squared G equals 0 for all P equal to 0. So this is the 5. Okay, which governs the time evolution of the displacement. And one PDE, the f of xx plus f of y minus kf equal to 0 for all xy in R. Alright, and so this PDE governs the amplitude of the vibration. Okay. Now for the PDE, next let the special component into h of x and q of y. Okay, and substitute it into the PDE here to obtain. So we have the Q here and d square h of x plus h d square dy square of q y minus k and h and q equals 0. And now if we divided the equation by q times h, then we have for 1 over h and d square dx h of x equal to 1 minus 1q and d square dy square q minus k q equal to p. Okay, where p is a constant. So that's good. So we have that. So now let's we obtained two ODEs. Right, so the first one would be so d square h dx square minus ph equal to 0. Okay. Okay, and the d square q dy square minus k minus p Okay, mass K minus PQ equal to 0. Alright, so now we have another two ODEs. And the boundary conditions, the boundary condition in 12.9 point 2 here is boundary condition. Says that okay, so u of x, y, t equal to h of x, q of y, and g of t is equal to 0 for all x, y in the boundary of the rectangle, and equal to 0. Now, since g of t is not identical to 0 for all t equal to 0, okay, so g is not identical to 0. Because if g of t identical to 0, then we have a trivial solution, okay, which is not interested. So, alright, so we have so some p g of t is non-zero, okay, and so that the product should be 0. Okay, so that so we must have h of x, q of y should be 0 for all x, y in the boundary. Okay. Okay, and which render two boundary conditions okay for the ODE in this one. Okay, for this ODE. And so what this means that H0 is 0 and H of A must be 0. Okay. So this is 12.9 and the two boundary conditions for the ODE in 12.9.8. So the Q0 is 0 and the QB is 0. Okay. In order to have non-trivial solutions u, x, y, t. Or things, maybe I will say things, both either is not identical to 0. Okay? And so we have two boundary conditions. Okay, so these two ODEs, each ODE has each of these two ODEs has two boundary conditions, and so we can solve for them. Okay, and now so we consider this one. For P greater than or equal to 0, there is no non-trivial solutions. For the ODE in 12.9.7 together with the two boundary conditions in 12.9.9. Okay, as before, we will talk about this kind of situation many times. Okay. And similarly, for K minus P greater than or equal to 0, okay, there is no non-trivial solutions. Actually, for the ODE in 12.9.8 together with the two boundary conditions okay, in 12.9.10. Okay, so then K minus P is greater than or equal to 0, then we have no non-trivial solutions, satisfying the ODE and also the two boundary conditions. So now we consider P equal to minus mu square, which is negative the original solution of 12.9.7 x here, h of x equal to a cosine mu x plus b sin mu x. Alright, now h of 0 is 0, implies a equals 0. And h of a equals 0 implies that b sin mu a is 0. Okay? And so b not equal to 0 implies that mu should be equal to n pi divided by a and greater than or equal to 1. Okay. So that's a solution of 2.9.7 together with 2.9.9 with P equal to minus m pi divided by a square. X here is equal h of m, which is sine m pi x divided by a for all m greater than 1. Okay, so for a countable many for a countable many p, okay, with parameter m here, that we have a solution there. Okay, so we have got countable the many solutions. And the next, consider k minus p equal to minus nu square, which is negative, nu is positive, and a general solution of, a general solution of 12.9.8, okay, is qy equal to c cosine nu y plus d sin nu y. Okay, and so q 0 is 0 implies that c is 0, and the q of b equal to 0 implies that d sine nu b equals 0, and the b not equal to 0 implies nu is equal to n pi divided by b for n greater than 1. Okay, so that's a solution of 12.9.8 together with the boundary condition in 12.9.10 and with k minus p equal to minus n pi divided by b square. Right, is q sub n of y equal to sine n pi y divided by b here. Okay, so up to now, that everything is quite standard when we use the method of separating variable. Now, since we set p is equal to minus m pi over a square, and k minus p is equal to minus m pi divided by b square, then we have k, which is just the sum, okay? And now we have minus pi square and m square divided by a square plus n square divided by b square. And this will be used to solve the first ODE we obtained, which governs the time variation of the displacement. Okay, because we have K here, right? K here. Okay. Right, and the ODE in 12.9.5, okay, 0.5 there. So this ODE becomes, okay, so now so this ODE becomes G dot dot plus C square pi square M square divided by A square plus N square divided by B square, and the G equal to 0. Okay, and which has a general solution we call GMNT. Okay, equal to E sub NM cosine lambda Mn T plus E Mn star sine lambda Mnt for all t greater than 0, and then where lambda Mn is defined to be C pi and the square root of M squared divided by A squared plus N squared divided by B squared for all M, and in the set of all positive integers. Okay, so we have this one. Okay, so we now find infinitely many solutions of the two-dimensional wave equation in 12.9.1, and is satisfying the boundary conditions in 12.9.2. Okay. So that U Mn x y t is equal to G Mnt H Mx Q My. So this is equal to E sub Mn cosine lambda Mnt plus EMN star sine lambda m n t sine n pi x divided by a and the sine n pi y divided by b. Okay, for all and for all n in a. Right, so these solutions, right, may not satisfy the two initial conditions. Okay, even though they satisfy the boundary conditions, okay, but they may not satisfy the two initial conditions. Okay, and these solutions so U sub m and so this will be called an eigenfunction of the vibrating membrane corresponding to the eigenvalue lambda sub mn, which is c pi square root of m squared divided by a squared plus n squared divided by b squared. Okay, and subject to the wave equations in 12.9.1 and the boundary condition in 12.9.2. Okay. All right. So these are eigenfunctions. Okay, corresponding to eigenvalues here. So this is the angular frequency, as you can see, right in here. So that is the angular frequency you have. Okay. Okay, so this is the angular of the eigenfunction U sub mn. It's possible that we may have a different combination of mn with the same lambda, okay? Because you have two parameters here, right? For example, n equal to 1 and equal to 2. The other is m, okay? So m equal to, say, 1, m it depends on A and B, okay, of course. So for example, if A and B equal to 1, for example, A and B equal to 1, then n equal to 1, n equal to 2, or n equal to 2, n equal to 1, right? They will have the same lambda, but with different mn combination. Okay, and as you see that if mn are different, then you have different eigenfunctions. So it is possible that the eigen value is degenerate because that it corresponding to more than one eigenfunctions. It's possible. Okay, it is possible. But we want to solve our problem, because our problem including two initial conditions. Okay. Now, so we will use superposition. Since both the wave equation in 12.9.1 and the boundary condition in 12.9.2 are linear and homogeneous. Okay. A superposition of eigenfunctions must be a solution of 12.9.1 and 12.9.2. Okay, so let's write down the superposition here, and it will be a double sum. So this is okay. So we have this superposition here, and so we will determine the coefficients E sub mn and E star sub mn, so that the solution so this is about 12.9.11. Okay, so solution in 12.9.11 will satisfies the two initial conditions. in 12.9.3 and 12.9.4. Alright, now first of all, by 12.9.3, right, about initial displacement, we know the initial displacement is equal to and when we put t with 0 here, now so this is 0, okay, and this is 1, so we have E sub mn, and times the sine of m pi x divided by a, sine of n pi y divided by b. Okay, so we have this one, and so actually this is which is the double Fourier sine series expansion. So this is the double Fourier sine series of the initial displacement. Okay. And the idea is just a direct extension of the Fourier sine series of a function of one variable, because here we have a function of two variables, okay, and define on here, okay, an interval of x as well as an interval y here, okay, and so we can determine these coefficients in the following way. Okay, so to determine the coefficients, E sub mn, so we first fix y in 0 to b, okay, and regard, okay, so this one, regard 12.9.12 as the Fourier sine series of f of xy with respect to x, i.e. we do this okay, so we fix y, so we regard this as a function of x only, and so that we have y sine m pi x divided by a, okay, and where E n tilde y is equal to n equal to 1 infinity e sub mn, and the sine n pi y b or y b here. Okay, so we just together. This is defined as, this is a function of y, right? Okay, depends on y. So if y is given, then of course this is, so if y given, this is a number we have here. Alright, and so this function y can be computed by here. So e m to the y is the 2 divided by a, 0 to a, f of x, y, and sine n pi x divided by a dx. Okay. Okay. So this is just the Fourier sine series expansion of f of x when y is given. So as a function of x. Okay. So this. So we have this one here. Okay, but we know from here, this one, this is the Fourier sine series of e m to the y. Okay. And then, so em n, okay, becomes 2, and the e to the y sine n pi y b dy. Okay. Right. So here, em n. So once we obtain the e tilde sub m of y, and because e tilde sub m of y has this Fourier sine series expansion, okay, so e sub mn can be obtained by this formula, and so this is actually so this is b with and f of x y sine n pi x a dx and sine n pi y b and dy. Okay, so in this one, you do this is iterative integration. So you have you integrate over x first and then over y. But this is equivalent to, you do the other way, you can do the integration. So from y first and then x. So either or will be fine, and so that we can write down. Okay, and dx dy. Okay, we can write down this as the surface integral or double integral there. Okay, so you can write it as double integral. The evaluation of the double integral can be done in two ways. Into iterative integration. Yeah, either first with x and then with respect to y, or first with y and then with x. Either way will work. So you will have that. Okay, and so you determined the coefficient E sub mn, right, by using one of the two initial conditions. Right, and then, so this is from the initial displacement. Now with the initial velocity, okay, so next, the partial derivative of u x y t in 12 Okay, so maybe I need this one. So this is 12, 11, 12, and 13. Oh, sorry. I don't need this. I confused. I'm sorry. I do the correction. Okay. So that here, this one. Okay, so in 12.9.11. Okay, so this equation. So the partial derivative of the superposition with respect to t is here, ut x y t, which is in here. Okay, so here we assume we can exchange the order of the operator and the double sum, the double summation. Okay, and which should be justified later on, but for this moment we can just assuming that we can exchange the order, and so that's okay. So this is becomes 2 minus lambda mn e mn sine lambda mnt plus lambda mn e mn star cosine lambda mnt sine n pi x divided by a sine n pi y divided by b. Okay. Okay, so this is the partial derivative. So this is described the velocity of the displacement at any time, and so by 2.9.4, so by initial condition for the initial velocity, so we have the g of xy, which is yield sub t xy 0. So this becomes 2 lambda sub mn e sub mn star, and the sine n pi x divided by a sine n pi y divided by b. Okay, and which is the double Fourier sine series of the initial velocity g of xy. Of xy. Okay, so now, so with a similar argument, so we have that lambda mn e star mn is equal to okay. So which implies that the EMN star is 1 over lambda mn to A to B. Right, so we conclude that So we can include that. The U, X, Y, T in 12.9.11 here with EM and EMN star in 12.9.13, 12.9.14. Okay, satisfy the two-dimensional wave equation in 12.9.1 together with the boundary condition in 12.9.2 as well as the two initial conditions in 12.9.3 and 12.9.4, provided that the series in 12.9.11 converges. Okay, and the series of termwise partial derivatives corresponding to partial converge to the corresponding partial derivatives of the sum U, X, Y, T. And 12.9.1, 12. And the two-dimensional wave equation in 12.9.1 is satisfied. Okay. Okay, so let's take a break up to 2:40. Okay. Okay. So we solved the two-dimensional wave equations for the rectangular membrane, okay, in the XY plane. But how about if the membrane is not rectangular anymore? Okay, so the membrane now is circular. So let's say is this okay, and the radius is, say, r. This time r is the radius. Okay, so now consider a two-dimensional circular membrane. For example, the drum head. So that's circular vibrating membrane. Okay. Right. Now, so the region is here, XY, such that okay, and the membrane has the points in the circular membrane, right? Basically, they are related, right? So that they satisfy this linear inequality. Okay, and for such a problem that it would be hard to use the method of separating variables. Why? Because in regular, in the rectangular vibrating membrane, we have for that XY and this can be written as the Cartesian product of two intervals. Okay, so that the defining, the region, okay, of the two-dimensional equation is on such a Cartesian product. And because of that, the Cartesian product we have, so that we can do the separating variables, because the x and y here can be, x can be freely, okay, chosen in between 0 and a, and y can be chosen freely in between 0 and b. Okay, so that separating variable becomes to be sensible. Okay, but in here we can't, because this circular region cannot be expressed as the Cartesian product of a subset in the x-coordinate and a subset in the y-coordinate, we can't. Okay. Alright, and so a way to resolve this problem is that so an idea is to use a coordinate transformation right to map the circular membrane in the xy plane right to a rectangular region in a new EV plane. Okay, so that is the idea. Okay, and a way to do so is by doing the polar coordinate. So here, so we are familiar with that. Okay. So for each point, the P point, xy here, we have an R and a theta here. Okay. So that the R theta give us 2, and the R is equal to okay, and the theta in here we use arctangent, so we use and the theta arctangent divided by x, if x is greater than 0, and the arctangent of x plus pi, if x is negative, and is pi over 2, when x is 0 but y is positive, minus pi over 2, if x is 0 but y is negative. Okay. Alright, and so that this is R. Okay, this is a theta. And the R will be here. So up to okay, and here is R. Okay. So the region, the circular region, becomes to okay. So this is actually it's the so we can puncture the origin, okay, because for the origin the theta is not uniquely defined, okay, so that this is okay. All right, and so the region becomes 2 this one. So we have okay. You can see that now the region by the polar coordinate. So this is the polar coordinate theta. You transform a circular membrane into a rectangular membrane. Okay, and now in the rectangular membrane, you can apply the method of separating variables again, as we will see. Okay, so this is the idea. So the reason why we use the polar coordinate transformation is that now the wave equation is defined in a rectangular region in the new plane, in the new R theta plane here. Okay? But with that, we have to transform the two-dimensional wave equations in the xy plane to a corresponding PDE, okay, in the R theta plane. Okay. So we have to do what we have done in the section 12.4. Okay, in 12.4, we have used basically characteristic curves, okay, to find appropriate coordinate transformation, at least locally, right, to transform a semi-linear PDE to normal forms. Okay. Okay, now okay, now the two-dimensional wave equation in the xy plane, x here, c square right. So now the polar coordinate transformation from to the third plane. X here is that xy equal to, and as I have written, and the inverse transformation. So actually we can write it to 0 to infinity, and okay, so this. So the inverse transformation is xy. So this is from 0 to infinity. Go back to, alright, and here x theta is r cosine theta, y r theta is r sine theta. Okay. So this is the inverse coordinate transformation we have. Yeah. The reason why we choose tangent is because, as we know, here. So this is tangent. So we see that the tangent function is a periodic function with period pi here. Okay, it's period pi. So our tangent is usually defined, okay, with the range from minus pi over 2 to pi over 2, okay, to pi over 2. So this gives us the angle in between minus pi over 2 to pi over 2. Okay, and this corresponding to that x is positive. Okay, because that the angle here, you see the angle, if the angle is in here, you see the x-coordinate always positive. Okay, and so if x is negative, then you have to go to there. It's about the third and fourth quadrant of the plane. This is third, this is the fourth, this is the fourth. The second and the third. And, okay. So that in these two quadrants, the x coordinate is positive, but in these two, the x coordinate is negative. Okay. So you have to add a pi here, and the other two is pi over 2. If x is 0, you can see x is 0 is not defined. So when x is 0 and y is positive, you get to pi. So it's here. But if x is 0, y is negative, then you have minus 2 pi here. And minus pi over 2, sorry. This is pi over 2 and minus pi over 2 there. Pi over 2. Okay. All right. So you have the correspondence here. You have this coordinate transformation. Alright, so we let U tilde I say T to be U x theta, y theta, and T. Then we have, so we can return back x u by u tilde and r xy and theta xy and t here. Okay, so we have this one. Alright, and so by the chain rule, okay, we have u of so the partial derivative with respect to x. So now you will have u tilde r and times r sub x plus u tilde theta, not theta x here. And uxx comes to so you can do that is u r, okay, and so we can do here u x, take the partial derivative and use theta x here, and this one. So now you can take the partial derivative with respect to u tilde r, so that you have u tilde r and r sub x tilde r theta x times rx plus u tilde r xx. Okay, this one, and plus that the u that's theta r x plus u theta theta x theta x plus u theta and theta xx. Okay, so there are these terms we have. And in here we need the partial derivative of r with respect to x, partial derivative of theta with respect to x there. Okay, so now also we will do it because the Rx is equal to x divided by x squared plus y squared, so that is x divided by r here, and we write so that this is equal to 1 over x squared minus y squared, because theta is the arctangent, and we know the derivative for arctangent is 1 over 1 plus the argument square. Okay. Alright, and so this is minus y and r square. Okay. So we have this derivatives can have. Alright, and we need so what we have, we need xx. Okay, so now we have minus x x and r square, so this is y square and r third power, okay, by the quotient formula, okay, because r is a function of xy, so you have this, and theta xx, theta xx it's right here, so we have minus y, and so this is minus 2 third power to x here. So this is become 2xy and r to the fourth square. Right, so you can do the substitution. So you can substitute everything so that uxx becomes 2x square r square u2 r minus 2xy divided by r third power u theta plus y square fourth power u theta theta plus y square third power u theta plus 2xy and r fourth power u theta theta. Okay, we have this. And similarly, right, we can So we could follow similar procedure. So we find this is y square r square u r theta plus 2xy third power u theta r theta plus x square fourth power u theta theta plus x square third power u r theta minus 2xy fourth power u theta. Now when you add them together, right? So the Laplacian of u in the polar coordinate system is here. So uxx plus uyy. Okay. You add them together. So when you add them together, you see that x square plus y square is equal to r square. Divided by r square, this is 1. So you have r theta. And the second term cancelled, so they will cancel them. So they cancel, and the last term cancel together. And the second here, you get 1 over r square into the theta. Okay, and the last one is 1 over r u theta. Okay. Alright, and so the two-dimensional wave equation in the r theta coordinate system becomes to u theta theta t equal to c square r square and u theta theta t plus 1 over r u theta plus 1 over r square and c square is okay for all okay theta in for all t 0. Okay, so this is our two-dimensional wave equation. Okay, so this is two-dimensional wave equation we have. Okay, all right, parenthesis here. So we will deal with this two-dimensional wave equation in the r theta coordinate system. Okay, and we are imposing that proper boundary condition as well as initial conditions. Okay, and then you will see we can apply the method of separating variable again. Okay, so I'll stop here.